Today we are going to discuss about the magnetic effect of electric current. Okay. See, electricity and magnetism, these were considered as two different topics earlier. Okay, electricity was a different topic and magnetism was a different topic. But later on, with one experiment, there came a new idea that actually electricity and magnetism are interconnected. Okay, so electricity and magnetism, which were considered as two different subjects, by one experiment it was proved that electricity and magnetism are actually interlinked, interconnected. Okay, and this experiment was really a milestone in the field of physics. Okay, and this experiment was carried out by one British scientist. His name was Oersted. So James Christian Oersted was the scientist, and what he did actually, he was demonstrating Ohm's law to his students, and while demonstrating the Ohm's law to his students, what happened that by some error there was one magnetic needle compass kept near to the current carrying conductor. He observed that when the current passes through the current carrying conductor, compass shows deflection. Okay, and see, nowadays it is very easy to say, because you also studied in 10th standard the same thing, so very easily you can say that because there was magnetic field around the current carrying conductor, and because of that the compass needle deflects. But at that time it was not so easy to predict this, that it might happen. Okay, so there was a current carrying conductor and a compass needle was getting deflected by that. This was something very strange. Okay, now a current carrying conductor, if it is there, then it is carrying current, that is the stream of electrons or stream of charged particles. But here what was happening, that a compass which is kept near to the current carrying conductor was getting deflected. Now this was something, as I told you, that was very strange, and when they tried to explain it, definitely magnetic field can affect the magnetic needle, compass needle, but here there was electric field, there was current flowing through the conductor. And one more thing, that current also can flow through the continuous path like this wire, closed loop, but it can't flow through air like this, and it is not going to affect this in this way, that the magnetic needle gets deflected because of the current. So that was something really very very difficult question to answer at that time. Later on they came to know this, and they established a theory that actually what happens, that when a current flows through a conductor, there is a magnetic field around this current carrying conductor, and this magnetic field actually deflects the compass which is kept near to the current carrying conductor. Okay, so this was a very important experiment in the field of physics. Okay, Oersted's experiment. And then Oersted gave one rule. Okay, and that was a snow rule. Okay, so what is the snow rule? Let us discuss that. Suppose that there is a current carrying conductor, and current is flowing, say, from this end to this end. Okay, and there is a magnetic needle. Okay, here we have a magnetic needle. Here we kept a magnetic needle just below it or near to it. Okay, now this is the south and this is the north pole of the magnetic needle. Okay, now what happens, that when current flows through the conductor, okay, and here we have the magnetic needle. So what happens, that this magnetic needle, if the current is flowing from south to north, or in the south to north direction through the conductor. Okay, so south to north direction is this, because we kept magnetic needle like this, and you can see that current carrying conductor, through it the current is flowing from the direction south to north. If the current is flowing from south to north, then it is observed that, so this is the snow rule, SNOW, snow rule. Okay, what is it? If the current is flowing from south to north through a conductor and magnetic needle is kept just below it like this, so it is observed that the north pole always gets deflected towards the west side. North pole always gets deflected towards the west side. So you know this, that if this is the north, this is the south, this is west and this is east, so north pole gets deflected towards the west side. So deflection in this would be like this, that the north pole will shift this side and south pole will shift this side, so magnetic needle will deflect this side like this. Okay, so this is what the snow rule is. Okay, this is what the snow rule is. If you change the direction of the current, then the deflection would be in the opposite direction. Now the north pole would shift towards the, if the current is flowing from north to south, then the north pole will shift towards the east. So this is what the rule is. South to north, if the current is flowing, then the north pole shows the deflection towards west side. Okay, so this is what the magnetic effect of electric current is, that around a current carrying conductor there is a magnetic field, and this magnetic field can be detected, can be experienced by a magnetic needle or compass. Okay, so this is what we have, the magnetic field, okay, around a current carrying conductor. And this was a very important rule. Why? Because this rule proved that the electricity and the magnetism are correlated subjects. They are not different subjects, but they are interlinked subjects. Okay, now suppose that there is a current carrying conductor, and around this current carrying conductor, if we have to find the magnetic field direction, so the direction of magnetic field is given by right hand thumb rule. Okay, the direction of magnetic field is given by right hand thumb rule. Now what is right hand thumb rule? Suppose now imagine that you are holding a current carrying conductor like this. This is a current, say this is a current carrying conductor, and the tip of the current carrying conductor shows that the current is going upward. Okay, say this tip of the current carrying conductor shows that current is going upward. Now if you are holding a current carrying conductor like this, that the thumb points the direction of the current, thumb points the direction of the current through the conductor, then curl of your fingers will give you the direction of magnetic field lines around the current carrying conductor. Curl of your fingers will give you the direction of magnetic field lines around the current carrying conductor. Now you can see, if you do this, you should right hand, okay, if you do this, you will find that the direction of magnetic field lines is in anti-clockwise direction when the current is going up. So in this case, if you see that direction of magnetic field lines around a current carrying conductor, direction of magnetic field lines around a current carrying conductor is given like this, and it is anti-clockwise direction. Anti-clockwise direction means it goes like this. Okay, so this is the direction of magnetic field lines around a current carrying conductor. Okay, clear? So if it is going, current is going upwards, if current is going upwards, then the direction of magnetic field lines is clockwise, sorry, it is anti-clockwise. And if the opposite is there, suppose that the current is going vertically down through the conductor. If current is going vertically down through the conductor, then you would find that the direction of magnetic field lines, curl of the fingers will give you the direction clockwise. So the direction of magnetic field lines here is in clockwise direction. It is in clockwise direction. So this is what the direction of magnetic field lines around a current carrying conductor in which the current is going vertically downwards. So this is what the right hand thumb rule is. Right hand thumb rule. Right hand thumb rule. This is the right hand thumb rule. Okay.